Now we're going to finally look at sequences where we don't insist that every term of the sequence is positive in order to determine convergence of the series. So we are going to look at specific kinds of sequences, though, called alternating sequences, and when you sum them up, they're called alternating series. And the key part of an alternating series is that you have a positive part, and then you have an alternating part that oscillates between 1 and -1. It can start with negative or positive, but it alternates each term. When we have such a series, we have something called the alternating series test, which says if you just look at the positive part, right, then if that goes to 0, that's all you need to determine that it converges, which is a wonderful thing. Now, we should look at an example here, an important example, because we know that the so-called harmonic series, 1 over n, it diverges. Okay, that diverges. But what this says is if we were to look at the series n goes from 1 to infinity of -1 to the n times 1 over n, then we have this positive part, an is 1 over n. It goes to 0 as n goes to infinity. So by the alternating series test, the series -1 to the n times 1 over n converges. Okay, so this is an important caveat to this famous series where 1 over n, it diverges, but if we have an oscillating term, then it converges. So a thing that we can do with alternating series is actually figure out how many terms do we need to add up so that we can get a good enough sum. So let's take a look at an example. Let's find how many terms we need to go out, right? And it's find out how many terms we need to go out to be within 1/1000th of the actual limit. Now, with some fancy mathematics, you can show that the sum of that series is 7 pi to the 4th over 720. We won't show that. We'll just take that. But let's say we're doing a problem where we need to get close to that limit, whatever it is, but we don't need to actually find it. How many terms do we need to add up? The first 2, the first 3, the first 4, etc. So what I have here is a sort of brute force method. You might do this using technology if you just didn't have anything else to do. I went into Desmos and I just put in the function in this sequence, and all I wanted to do is just add them up, the first one, the first 2, the first 3, the first 4, and see how far away that is from its limit. And so as we can see, the first one, what we have here, this is the first sum, S1 minus the limit L. Okay? And what we have here is S2 minus the limit L, S3 minus the limit L. So what we're looking at is the difference of these partial sums away from its limit. And finally, we're getting close down here. This is the 4th partial sum minus the limit, so that's how far away it is, how far away the 4th partial sum is away from its limit. And then that's still bigger than we're looking to be within 1/1000th over here. And so we can see how far we need to go. We need to go n equals to 5 to get within 1/1000th of our limit. So that's the answer, sort of just doing it brute force with something like Desmos. And if we found the first 5 terms of the sequence, we can see it's 0.9475, whatever. And what's the actual limit if we were to sum all the terms together? It's this here. So we can see we can get very close, and not only can we get very close, we can get as close as we want to be and determine how many terms we need to go out. However, this is not in the spirit of the theorem. This is just sort of brute force, and this is actually very hard sometimes. So we want to find a better way of figuring out that the answer here is n equals to 5. So let's use the theorem. So this is what we need according to the theorem. We need an plus 1 to be less than epsilon. Okay, so let's figure out what we have and what we need. We can find the expression for an. If we go up to our alternating series, the positive part here is an equals to 1 over n to the fourth. Okay, so an equals 1 over n to the fourth. And we have that epsilon is equal to 0.001. So let's just find the n. Find n so that an is less than epsilon. We'll worry about the n plus 1 later. We just want to figure out, what does n have to be? Which part of the sequence do we have to go out to so that it's less than 0.001? Well, we can put this in. 1 over n to the fourth is less than 0.001. And if we solve that, we get n to the fourth is bigger than 1,000. And we don't need much technology here. We could take the fourth root of both sides, of course, and find that. But we can kind of do this in our head. What number to the fourth power is bigger than 1,000? Well, 5 to the fourth power, that's 25 times 25, that's less than 1,000, so 5 to the fourth power. But then 6 to the fourth power is bigger than 1,000. So this is 5 point something, right? It's 5.6 something something something, okay, is bigger than n. So what does this really tell us? This tells us that in this case, when we're finding n here, we need to have n be bigger than or equal to 6 for this to be true. So when n is bigger than or equal to 6, we have an is less than epsilon. Great. So what we need is to find n for this, though, because that's what the theorem says. If we go back up to look at the theorem, we want to find n so that the error, which is the distance from the actual limit, is less than an plus 1, because we want to go far enough so that that's less than epsilon. Okay, well, if n is 6 here, we just need to have n plus 1 being 6. So we need an plus 1 to be less than epsilon. Okay, so if we have n equals to 5, then what's n plus 1? N plus 1 is equal to 6. So therefore, an plus 1, if n is equal to 5, then for all n bigger than that, an plus 1 is 6. That's going to be less than epsilon. And according to the theorem, that is the distance, the error, which is the distance from the nth partial sum to the limit, is going to be less than that. So we've found our n. We've guaranteed that when n is greater than or equal to 5, that an plus 1 is going to be less than epsilon. So therefore, n equals to 5 is how far we need to go out in the sum to be less than epsilon. So this is the bulk of the work that we need to show for that. Now, another big topic of this section is absolute and conditional convergence. Absolute convergence means that if you were to take the absolute value of every term and add it all up, it still converges. Okay, that doesn't always happen. We'll see some examples. Conditional convergence means that if you were to take the absolute value of every term, it doesn't converge, but it converges if you don't. So let's look at some important examples here. This is the harmonic series. This famously diverges. Okay, well, what about negative 1 to the n over 1 over n? Well, we saw before that this converges. Okay, well, what about this one down here in the bottom? If we were to look at the absolute value of an here, that's going to be the absolute value of negative 1 to the n all over n squared, which is just 1 over n squared. But then the sum from 1 to infinity of the absolute value of an is just the sum, and goes from 1 to infinity of 1 over n squared, and that's a convergent p-series. This converges. So this series is absolutely convergent. Okay, meaning that it converges, yes, but even if we take the absolute value of it, it still converges. So that's what an absolutely convergent series is. This series is, it converges conditionally. Because if you were to take the absolute value of the series, then it does not converge. So conditional convergence means it doesn't converge if you take the absolute values and sum it up, and absolute convergence means it does converge if you take the absolute values. One of the last big results of the section is that if you have one of these absolutely convergent series, that means we can rearrange the terms and we'll get the same sum. And that's very handy sometimes, because if you're summing up an infinite series and the terms, you can group them in a clever way to find what the series is, then that's very useful. Then you'll know that if you sum them up, you'll get the same thing as the original one. If it converges conditionally, you can't do this. And it can be shown that if you have a conditionally convergent series, you can actually rearrange the terms to sum to anything. Okay, so that's a famous result about absolute convergence, and one of the reasons we want absolute convergence, because we can rearrange the terms and get the same sum.